Right, okay, so welcome everyone to this new video where we talk about stuff, physics stuff or mathematical stuff on the board. So what we are going to do today is basically try to see um, how we define a magnetic moment. And, um, and the thing is that the magnetic moment turns out to be defined when you actually have certain conditions that are met by the current distribution you want to look at. And likewise, in the case of the electric dipole moment, these are defined again in a set of conditions that are satisfied by the charge distribution. And then if these conditions are not satisfied, then basically you can't even define this particular moment. Okay, so here basically I list out this, and I'm going to go through them in a minute. So these are the conditions that we are going to look at, and then what happens is that we are going to obtain a relatively simple expression of the vector potential. And from this simple expression, then we basically extract the moment, the magnetic moment. So that's how actually things are defined, is that there are certain conditions under which, uh, regardless of the complexity, so that's the point, that regardless of the complexity of the actual current density, we can actually obtain um, a, a, um, a very simple expression that does not involve any integral, at least in the way it reads, and instead actually involves a sort of aggregate um, measure um, of um, of the power to generate magnetic induction fields. Okay, so that's kind of the idea, and that's what we are going to do today. Right, okay, so what we are going to do is first I'm going to delineate the conditions that we are looking at, and they are important. I'm trying to delineate them as clearly as possible. They are a bit mathematical, but that's electrodynamics, so unfortunately there is a bit of math going on. Um, Now, once we have set that up, then I'm going to go into a mathematical preamble that we need to cover in order to essentially make the expressions tractable and kind of compact and so on. So it's going to be requiring just your notion, typical notion of divergence and the divergence theorem. And if you know these things, then in principle it should be easy to follow. At least it should be followable. And then once we are done with this preamble, then we'll move on to quite quickly, in a sense, try to determine then the expression for the vector potential that is generated by a localized charge current density. Okay, so that's the program. There's quite a lot to cover. Um, Hopefully, it's going to be less than half an hour, and we'll see how that goes. Okay, so first of all, the conditions that we are looking at. So I'm not going to cover every possible situation. We are looking at a case where the current density is actually localized. And mathematically, what we mean by that is that there is a domain of the three-dimensional world that I'm calling here omega, and that basically J belongs to that domain. And what that means essentially is that J is zero outside of that domain. So I can basically limit myself to integrate over that particular domain, and then I'm done. Now, because J is also assumed to be continuous, then what that means is that we are going therefore to assume that at the border of omega, so sometimes denoted that way, so with some d here omega, J is going to be strictly zero as well, because it's zero outside of omega. So if we assume continuity and we assume that this is, let's say, a closed kind of set, then d omega J would be zero there. We assume, I mean, it's more than an assumption, it's kind of a principle that there is charge conservation going on. And basically that relates to this continuity equation where rho here would be the charge volume density. And then here that's a divergence of the current density that probably you've seen before, or if not, then please don't hesitate, by the way. If there's anything that is that you don't understand or you would like it to be covered in some shape or form, then I'm happy, of course, to go through it. So that's the traditional kind of differential manner of characterizing charge conservation. And in fact, I probably will do at some point a video on how to derive that quantity. Um, but then, because we assume here, that's one of the conditions, that we've got a pure current, so there is no net charge density rho anywhere, rho is zero everywhere in this particular discussion, then obviously d rho over dt is going to be zero as well, and consequently the divergence of j, is going to be zero. And that's going to be something important later on, so that's why I'm saying it here. Um, and finally, we are interested in a point, so that located from some origin that we put like the origin. Usually we put it somewhere in the charge distribution. So within omega, we put the origin, but then we look very far away from it. Now, aside from this, I'm going to use different notations depending on what I'm going to do. So R here is the vector position where I want to know my magnetic field, or here that would be the vector potential, and then I'm going to is going to correspond to the coordinate x, y, and z. But at some point, I will have to actually use some other notation, and I'm going to use the notation x1, x2, x3, because then I can use an index I to refer to any of the possible x, y, and z. Okay, so just be mindful that I'm going to make these changes from time to time. And finally, we are going to then try to find out then what is this expression for a simple expression for the vector potential. Okay, so that's the conditions that we are working with, and that's what we are going to use, in fact, in this kind of preamble here. So by the way, I want to say, because there's no reason kind of claiming that this is my own, this is basically a sort of a bit more detailed version of a derivation proposed in the classical Jackson's textbook in electrodynamics. So it's not necessarily, it's not from me per se, at least not all steps, but then here I try to specify some things that, in my opinion, are not specified enough in the derivation in the book. Okay, so first of all, we are going to start by saying that if we have any function, or any two functions, f of r and g of r, okay, so if we take any two functions, f of r and g of r, then what we can say is that we can try to look at the divergence of f times g and then times j. Okay, so fg j is a field, is a vector field, and so I can apply the divergence to it. Now, this looks kind of complicated, but here I'm going to use something quite natural, which is basically that the divergence of a scalar field times the vector field is equal to the scalar field times the divergence of the vector field, but also it's equal to the gradient of the scalar field, and then dot product with j, the vector field. Now, because here I've got the product of two scalar fields, I need also to use a product rule, and so I will have two terms like this. So the bottom line is that if I do this, I'm going to get the following. I'm going to get fg, then divergence of j, then I'm going to get plus f, and then gradient of g dot j, and then plus g, and then gradient of f dot j. Okay, so that's basically what we obtain. There are multiple ways of getting this. Again, if you use the typical identity I mentioned earlier, then you will get there. You can use as well tensor notation if you want. Again, if this is something you would like this to be covered here, by all means, do let me know, and I will cover that. How to do that very easily. Let's say with tensor notation. So one of the things here is that if I try to say, okay, let's look at the integral, I'm just going to write a single integral here over omega of the divergence of fgj and then dv. I hope you can see, by the way, because I know that there are plenty of things coming up, so that's why I don't write too big. Then I can use, provided f, g, and j and their divergence are actually all defined within omega everywhere. Okay, so that's a very important point. Maybe later I will come into some more details about this stuff, but provided all of these terms are defined in omega, then I can use the divergence theorem. And so there's going to be the integral over the border of omega of f, g, j, and then the dot product with the surface area. So I'm going to call it S here, just because A is going to be used for the vector field, for the vector potential. Okay, now I've got this, but keep in mind that J here is equal to 0 at the border of omega, okay? Because again, this is a localized current, and consequently, this is equal to 0, okay? So what we have in the end is that we are going to have the integral of omega is equal to, the integral of fg divergence of j and then plus f grad g dot j and then plus g grad f dot j and then dv is equal to 0. Now, to be honest, I could have already directly set that to 0 because I said that it was 0. So the divergence of j is also 0. So the bottom line is that we are going to have, for any f and g, we are going to have this relation that is equal to 0. Okay? And because it's true for any f and g, then we can try various things here. And in particular, I'm going to choose a first case where I choose f is equal to 1 and g is equal to one of the coordinates that I'm going to call xi. And here I'm going to say I is equal to 1, 2, or 3. Okay, so I just consider this and then I substitute. Okay, so if f is equal to 1, so I just have f1 here, then the gradient of xi is basically is 1, but it's 1 only for in the direction of xi itself. Okay, so so basically it's 1, but only in the direction of xi itself, and then it's 0 everywhere else. And then here gradient of 1 is 0. So the only term non-zero is this one. And so what is going to return is the following. It's going to return the integral of omega. Again, that's a volume integral, so that I don't want to take too much space with triple integrals. So I'm going to get here, I'm getting 1. Then the gradient again of, let's say, actually, let's calculate it here. So the gradient of xi is basically how to put it? Well, that would be the sum, okay, of I ranging from 1 to 3 of dxi and then dxj, and then here in the direction xj. Okay, but you see that if xi is not equal to xj, that's a delta function. Okay, so what we get in the end is that we are going to get 3, and here that's a delta ij, so that's a Kronecker delta, which is 1 when I is equal to j, and that's 0 otherwise, and then xj, and in the end, basically simply xi, right? That's what it is equal to. Okay, so basically, if I replace that with the dot product, I've got xi dot j, and basically that's simply returning ji. So the eth component of j, and then dv. Okay, and because this is basically this expression here, this is equal to 0. So I've got that if the divergence of j is 0 and j is 0 at the border of omega, then basically the integral of ji is equal to 0 as well. So that's a first result here that we can put. And then the second thing I'm going to do is we are going to look at f is equal to xi, and then g is equal to xj. Okay, so they are in principle different components of the r vector. So again, this is going to be true as well. So what we are going to get if I substitute, I'm going to get that the integral over omega, and then here I've got something like this, xi, and then gradient of j. So let's say this is f is equal to xi, then this is gradient of g, so that's xj. So that's going to return actually j and then j here. So that's the jth component of the j current, and then I've got plus xj and then ji, okay, and then dv, and that's actually equal to 0. And basically here at that stage, I'm basically done with the mathematics I wanted to talk about, so the calculus preamble, if you will, but that's specified, specifically for this particular context. Now, let's move on then to determining the, so let me check one thing. I just need to check um, if we see correctly what's going on here, and I think we don't, so let's try to see a bit better here. So now what we are going to look at here is the vector potential. So I'm going to use the Biot-Savart law, but for the vector potential. Okay, so for the vector potential, we've got A of r, and that's equal to mu naught over 4 pi, and then that's the integral, again that's a volume integral, and then over the totality of omega, and then that's j of r prime, because it's not the same, now we've got r, which is from some domain. If you want, I can try to draw what's going on. So here you've got some kind of domain where there is some j going on, and then you've got some origin there, and then you've got a point r here. So that's the vector r that is pointing anywhere outside and very far away from the distribution, and then any point inside the distribution is r prime. And so what I want to do is integrate over all of r prime to get the totality of the contributions to the magnetic field at point r here. So so that's basically what we have, and then this is divided by r minus r prime, okay, and then dv prime. So that's the expression. It's slightly easier than the expression from Biot-Savart for the magnetic field, so that's why I'm using here directly the vector potential. And usually what we need to do is try to calculate this stuff here. And this is not too complicated. What we are going to say is the following. We are going to say that 1 divided by r minus r prime is equal to, and so we need to be a bit careful here. We need to have, so that's, we could view it this way. This is r minus r prime, and then I can write that this is with the dot product with itself, okay, and then the whole thing to the power minus 1/2. Okay, so that's what we can try to do. Now, if you actually evaluate that stuff, or at least expand the brackets here, you're going to find that this is r squared, then plus r prime squared, and then minus 2 times r dot r prime. And all of that is to the power minus a half. Okay, so what we do when we are at that stage is we extract actually the r here from the expression. You need to keep in mind that there is a minus a half. So when we do that, we're actually going to get 1 over r, okay, and then multiplied by this quantity, so 1 minus 2 r dot r prime divided by r. Just trying to make sure I'm getting things right. Yeah, I think that's all right. Divided by r squared. Yeah, there you go. And then we've got then plus r prime squared divided by r squared, and to the power minus a half. And now what we are going to do is actually do a Taylor expansion, assuming that we've got r prime over r, which is much smaller than 1. So if we do that, then we are going to get the following. It's 1 over r, and then that's basically 1, and then times, 1 plus 1 plus, and this, and here I need to say minus a half, so that's coming from there, and then times 2r dot r prime over r squared. I'm going to stop here and actually say that any other term is of order r prime squared over r squared. So you see here, I actually keep the order to be r prime over r, and not any higher order in terms of the expansion. Okay, so that's basically what I do here. Again, the minus a half here is stemming from the first order of the Taylor expansion. And by the way, here there was a minus, so that's minus. So the bottom line is that we get this is 1 over r, and then plus r dot r prime divided by r cubed. Okay, because now the 1 over r is going to be multiplied here. Okay, so basically that's what we have. And now what we can do is actually say, well, therefore a of r is actually going to be equal to mu naught over 4 pi. And then I'm going to have the integral, so in fact I would say over r, so that's the first term here. And then I've got j of r prime dv prime, and then omega. So that's the first term, and then I've got a second term, which is plus mu naught over 4 pi, and then r cubed, and I've got the integral of omega. And then this time I've got something more complicated, which is r dot r prime. No, that's okay, I can keep it like this. And then multiplied by j. J, by the way, here is evaluated at r prime. We need to be careful here. And then dv. Okay? So here, these are two very important equations. And in fact, I'm going to call that equation 1 and here equation 2. Okay? So why do I write this? Well, because here, actually, we see that this quantity is actually equal to 0. Okay, and that's from equation 1 that we've derived earlier. So this particular equation is equal to 0. And then this one, we need to evaluate it a bit more thoroughly. Okay, so what I'm going to do is that I'm going to name this integral. And please keep in mind, this is dv prime. This is a vector integral. So what that means is that this is a scalar product. So that's a number, this thing. And j here is the vector part for it. Okay, So what that means is that a is going to have the direction of this integral over j. Okay, so that's basically how this is going to work, and that's how I'm going to frame the equation. Now, of course, I will need at some point to erase on that side to continue the calculation. But what's going to happen is that I'm going to look at the eth component, so ai of r. So I'm looking at the eth component of a, and that's going to be equal to, yeah, so that's before I actually do that. So what we see is that the eth component is going to be mu naught over 4 pi r cubed, and then the integral, and I'm simply writing here the scalar product, but like completely. So that's the sum, I ranging from 1 to 3, and then we've got xi, x prime I, and no, let's use j, sorry, let's use j, and that's j here, and then we've got here gi, and then dv prime. Okay, so that's the expression we have for the eth component of a. Okay, so I'm going to continue the rest on this board, so I need to erase this part here. So we are still calculating the magnetic moment anyway. So let's keep magnetic moment here. And then what's going to happen is the following. What we can say is that we can, if we want, we can take out, at least for the time being, we can take out the xj here. But again, ji here depends on r prime. Okay, so that's really important. So it's to be integrated over the primed variable. So I'm going to have ai of r is equal to mu naught over 4 pi r cubed. Then I'm writing the sum. Let's write the sum here. So that's j is equal to 1 from 1 to 3. Then the integral over omega. And then what we are going to, I put the xj here. And then I've got x prime j. And then let's put here j I. And again, that's interpreted as here, this is r prime, and then dv prime. Okay, but that's where this becomes interesting, right? Because this is going to be, I can use that to write something meaningful. And so what I'm going to say is that this quantity here, I can write it in a silly fashion as being half of xj prime ji dv prime plus half of the same thing, right? So nothing crazy here. I'm just saying that half and half is equal to 1. Okay? But then I can actually use this particular kind of theorem, if you will, or identity, to say that this quantity here is actually minus xi prime. So that's this quantity here is the integral. In fact, it's minus xi prime j, and then dv prime. Okay, so then what I do is that I put everything back together, and I'm going to get, this is mu naught, and then 4 pi r cubed, and then the sum of j equal from 1 to 3, and then I've got xj, and then I've got this half, the integral over omega, and I've got xj prime ji minus x prime I j, and then dv prime. Okay, So to be honest, we are almost done at that stage. What we need to do is try to understand what we have here. So um, what you notice is that here I've got a sum of a j of xj x prime j. Okay, so this sum corresponds actually to the dot product between r and r prime. Okay, likewise here I actually have xj with jj, and this particular sum here corresponds to the dot product between r and j. Again, j evaluated at r prime, so within the integral. So the bottom line is that what I get if I want to express the vector again on its own, so a of r, is going to be like this. And I'm just simply interpreting what I'm reading here. I'm not doing any calculation whatsoever. I'm simply interpreting these components into what they look like as vectors. And so what I get is basically I've got this half here, and then I've got the integral over omega of, so as I said, we've got the dot product of r dot r prime, and then that's multiplied by j. So by the way, this is what we used to have, okay, r dot r prime, but here it's actually in a half part, and then I've got minus, and what I have is that I've got j dot, so I've got r dot j, and then here that's r prime. Okay, and then the whole of that is integrated over the volume element. Now, as it turns out, um, there is a relation, that a mathematical identity, so math identity, and that says that if you've got A cross B cross C, then this is equal to B times A dot C, and then minus C, and then A dot B. Okay, so that's a mathematical identity. So here I can look at what I have. J appears to be looking like B, right? There's the same role as B because it's a plus J R dot R prime. And then here R prime seems to have the same role as C. So what I have in the end is that I can rewrite this as A of R is equal to mu naught over 4 pi r cubed, and then I still have the factor half, and then I've got the integral over omega, and I can replace that as being, so we should be a bit careful here, so that's r, and then cross, and then that's going to be j cross r prime, and then dv prime. Okay, so the reason why this is very useful to write this in this form is because it's written as a product of an object. And this object here in front of the product can be put outside of the integral. You see, it's not that trivial to do it on that side, because here the product was a dot product with some item here, and if I were to put it outside of it, I would have a tensor that would be r prime j. R prime j would be a sort of tensor, and then I would have to, like, the object would be complicated. While here we actually managed to transform that into an operation between two vectors. So that's the reason why we actually did all of that stuff. Now, what I'm going to do is I'm going to change signs. So if you swap this, you get a minus sign, and if you swap this one, you get a minus sign as well. So all in all, what we are going to get is that A of r is equal to mu naught, and then 4 pi over r cubed, and then that's times, in fact I'm going to write it this way, times M cross R. And then here where I've defined M as being equal, so that's the definition, half the integral of omega of R cross J. And then dv prime. In fact, that's R prime, sorry, R prime cos J of a dv prime. And actually, that's it. We've got actually our expression here for the magnetic moment. Okay, and the expression, as you can see, it's very much simpler than this whole integral that seems to depend very much so on all possible details of J. Here, we just need to know that, or somebody gives us or calculates or whatever this particular quantity, and then it's a single vector. Okay, so you need to understand that here we've got a single vector with three components, as opposed to an actual field that is defined everywhere over infinitely many points that we need to integrate over. Okay, so that's incredibly simpler to have this particular expression, and so of course these two are very much very important. Okay, and they are not only important for this, but also because as you probably know, there is no so-called magnetic monopoles, and therefore most of the time if you look at magnets and stuff like that, the field is going to be characterized by a potential vector, a vector potential, which is like this. Okay, so that was quite a lot of things to cover, but essentially that's it. And what we are going to see in the next video is basically something interesting about what we can say about the feasibility of magnetism, depending on the kind of theories we look at.